Good morning, sir.
Hey, good morning.
Very good morning to everyone. I, Dr. Vishal Kumar Gaur, faculty in Department of Electrical Engineering, MNIT Allahabad. On behalf of organizing team of this faculty development program, once again I welcome you all in this today's second session of this FDP. Today we have Dr. Guru Raj from IIT Kanpur as a expert or a speaker of this session. So on behalf of organizing team as well as the participant, I warmly welcome our speaker, Dr. Guru Raj. Welcome, sir.
Thank you so much. It's my pleasure to be part of this. Dr. Vishal,
So
thank you
allow
so
me
much.
to briefly introduce our esteemed speaker to all the participant. Uh, Professor Guru Raj received a PhD degree in electrical engineering from IIT Roorkee in 2020. From November 2020 to September 2021, he was a postdoctoral fellow with IIT Roorkee. He is currently working as an assistant professor with the Department of Electrical Engineering, IIT Kanpur. His research interests includes renewable penetration challenges to the grid, machine learning applications to power systems, power converters for EV and its interfacing challenges, power electronics applications to power system, microgrid control and stability. He received POSOCO Power System Award 2021 for his doctoral work and Avsar Award 2021 from DST. So we are indeed fortunate to have him with us today to share his insight and expertise. With this brief introduction, I now invite Dr. Guru Raj to kindly deliver his lecture and take us through today's session. Over to you, sir. Guru Raj, sir, my voice is audible to you.
Audible, sir. Your voice audible. You are audible, sir.
Okay, thank you, sir. Dr. Guru Raj, sir, you can share your slide.
Dr. Vishal, it's audible. There were some minute adjustments.
Okay, sir. Okay, sir.
Thank you so much. It's my pleasure being part of this event. I just share my screen just a minute. Whether my screen is visible?
Visible, sir.
Yes, sir.
Thank you so much again. So the topic of discussion that we have taken for today is resiliency improvement using renewables and electric vehicles. I'll just run through different slides, giving introduction about or giving a background of what is this topic is all about. And meanwhile, I'll also walk you through some of the case studies that we are working on at IIT Kanpur, how to improve resiliency using renewables and electric vehicles. So welcome you again for this talk. Let me begin. You're free to stop me anywhere, wherever you feel asking some questions, or towards the end also we can take up some questions. So this is a table of content. So I'll discuss about, we'll start with the electric vehicles, types of EVs, what is the context in this country today of electric vehicles, charging infrastructure, challenges, impact of EV on the power system, some case studies. Then we'll take up the renewable part of it. Finally, some real-time simulations. Okay. What is the motivation towards electric vehicle? As you see, there are major challenges the current globe is facing, especially the high carbon footprint, right? So somehow or the other, there is a hope that if we replace all the combustion, wherever there is a combustion which is going on, IC engines, or in the transportation sector, or generation of electricity through thermal power plants and nuclear power plants, whatever way we can reduce the emissions, either through generation or through consumptions. So that is the most welcome. That is most welcome actually. So from the transportation sector, the IC engines, the efficiency is also less. Lot of combustion fuels, combustion, emission is there, and carbon footprint is quite high. So electric vehicles is expected to reduce this carbon footprint, provided the input for these electric vehicles will be from renewables. Otherwise, the current electric vehicle situation is such that we are charging from the conventional grid, which is not so effective because already there is a carbon footprint, and we are adding more carbon footprint to it because any unit that you consume, 8 to 10 times is what the kind of in fact, one particular case study clearly suggests 1 unit of electricity generation requires 1 kg of nearly 1 kg of carbon emission. So that's a huge mass basically. So if you are charging your battery 3.3 kilowatt hour battery or whatever, so then you imagine 3.3 kilograms of carbon is already dumped into the atmosphere. So that is a kind of volume that we are speaking today. And if we come out with a figure where we reduce this carbon footprint by charging electric vehicles through the renewables, then that makes sense, right? So in the tailpipe emissions, that's what I mentioned, and the maintenance cost will be less. So some advantage have been figured out, bringing electric vehicles more into the picture today. So lower running costs, low maintenance costs, zero tailpipe emissions, and the convenience of charging at home is another main advantage. Having said that, there are many more challenges that we have to solve that I'll discuss in my further slides. So need for EV, the main objective is to reduce the overall carbon footprint. As you can see in the slide, 196 countries, 2015 they have come together and they have taken this pledge that we will all work towards saving this planet by reducing the carbon footprint, right? So India also has a target of 2030 by 2030 500 gigawatt of renewables. By 2040 plan to replace the entire transportation sector into by electric vehicles. So the huge ambitions and targets are there, but the challenges are simultaneously um, shooting up. So we need to solve them. So the dependency on fossil fuels would decline. This is motivation. The peak loading of the grid can be reduced. So if you properly organize these electric vehicles in such a way that whenever there is a peak, you don't charge the vehicles. Rather, if possible, if there is a feasibility, we go for V2G operation. We'll support the grid. And during the off-peak hours, when the grid is light loaded, then the vehicles can be charged to the grid so that you can use it as a mobile battery to support the system. And the ancillary services can be rendered like harmonics, reactive power management, and all this stuff. But the most important topic, I mean, as aligned with this topic of discussion, we are going to discuss how EVs can brought in, uh, can be engaged to enhance the resiliency of the system. I'll also discuss what is resiliency first, and then how EVs can be engaged in that regard. So by doing all this stuff, as an end user, being a prosumer, I expect also some revenue flow happening. So this can also source of a revenue as such. So the types of electric vehicles can be categorized into four ways. One is the hybrid electric vehicles, where you have a small electric motor. The battery is considered to be a supplement. IC engine is still there. So you keep charging, either if you have electricity, you charge, or if you don't have a charging station, then use this conventional means of running the vehicle. So plug-in hybrid electric vehicle, it's a dual fuel and dual traction. And then battery electric vehicle, it's only run by the battery, and fuel cell electric vehicle where only hydrogen is being used. This is the context by 100%. Uh, this country is expected to replace all the conventional vehicles by the electric vehicles. The challenges, I've just listed few of them. So lack of EV charging points. This is a main concern, my dear friends, when we look forward for a long distance travel, right? So yesterday also we had organized a talk from a guy who had traveled around 10,000 kilometers or something like that across the country. So and he was sharing his experience how the kind of challenges he faced if on the way if couple of charging stations are not maintained properly, if there is no electricity, then followed by those charging stations, if there is any particular charging station, if it is functioning, then there is a huge pipeline of queue is there actually. So waiting time will also increase. And per EV, he was mentioning this point that per EV, I think the uh, per charging station around 200 electric vehicles are there today. So ideally it should be 1:10. Each charging station should cater 10 vehicles. So infrastructure is very clearly visible that we lack in infrastructure today in this country. And the high battery cost, I'll discuss in detail about the battery chemistry also, and high charging time because of lack of infrastructure. Typical users concern over long range travel, which I have already mentioned, some regulatory concerns as well. So in the Indian context, it's a pretty old data, but the graph is showing very clear indication that in spite of these challenges, consumers are seemingly interested to purchase electric vehicles. Otherwise, why we should spend time to discuss about electric vehicles? Because the whole country is also aggressively looking forward for some obstacles are there, and technological advancement is expected to remove those obstacles in years to come. So mainly dominated by three-wheelers. Though we have two, three, and four-wheelers, we all see three-wheeler rickshaws around the campus, around outside the campus also. Wherever we go, we see the electric vehicles. It's quite common, right? So, but simultaneously, this two-wheelers and three-wheelers are significantly high in number. But four-wheelers, the concern is, it's mostly restricted within city limits. So once the infrastructures are lined up, so then we may expect that number of four-wheelers may also increase. So these are the datas which probably I've taken from the Bangalore city. So you can see that how the figures are very clear indicating how the number of EVs projected, the purchase of EVs are quite high as compared to the date we are standing today. Yes. So this is a typical layout or a picture of a EV charging infrastructure. As you can see, most of the electric vehicles, are most of the electric vehicles have this feasibility of charging either through AC or DC. Whatever the new vehicles which are coming up surely have this facility. Either they give provision to you, they have a provision to get it charged either through AC outlet or a DC outlet. So on the way, especially for the four-wheelers, if you find DC fast charging stations, then somebody can, if they don't have time, then they can pick it up. Or the ideal way of charging a vehicle is slow charging. This is what end users concern is all about, because you don't want to replace your battery more often. That will add on to your cost. So the battery life will severely degrade if you keep on charging using a high ultra fast charging infrastructure, right? So slow charger is the best one, but sometimes you may have to use a high DC, ultra fast DC charging infrastructure also due to some lack of time or waiting time or whatever reasons. So, so the provision should be there for both of them. So this is what you see. There is a charging panel, socket outlet, and there is a plug to which a cable is connected, and the plug outlet is connected to another side of a cable is connected to a vehicle, right? So this is what is expected. So the charging level standards are level 1, 2, 3. We find 3.3 kilowatt chargers also quite commonly available today. So 19 point, this is mostly for the small vehicles, and 19.2 kilowatt or up to 60 kilowatt. We can see vehicles coming up. Four-wheelers are being given a chance to get charged. And level 3 is for high vehicles, like up to 280 kilowatt is what I see today. The charging infrastructure is available in this country. So ultra fast charging stations, DC charging stations. So this is the outlet of the cable, and that you can see, which is plugged into your vehicle. So combined charging station is a system, is a CCS mode of charging, is an open international standard for charging the electric vehicles. You see here for both for type 1 and type 2 chargers, these are used. I'll just discuss about the pins available and what they indicate. So this is a charging plug. You can see here there are 5 plus 2 7 for the single phase. There are 7 plus 2 9 female outlets available. So what are they? So if it's a 3-phase, then we have 3-phase line. Then there is earthing and neutral. And this CP and PP indicates the communication portals. That means they will lock the vehicle during the charging. The PP is used for that proximity pilot, whereas CP is used for communication with the infrastructure. Like if you are using a off-board charger, then you need to communicate with the charging panel, like how much current is available at that particular instant of time is being offered to the can be offered to the vehicle which has come in. So, and there is a handshake which will happen. There is expectation from a vehicle, and there is something which can be offered through the charging panel. Ultimately, there should be a handshake, right? So then eventually a time is fixed, charging current and pattern is given. So for that entire duration of 2 hours, 3 hours, or 4 hours, whatever duration, the vehicle gets locked to the charging panel and gets charged, and that is through the proximity pellet or PP. So the CP and PP, these are the communication channels, helps to maintain the charging protocol, right? And DC plus and DC minus, obviously, as it clearly indicates, that's meant for ultra fast charging. So the charging time, it's quite common sense, and being electrical background, it's very easy for us to navigate through this slide. So you all very clearly understand that the charging time will increase based on two factors. If the capacity of the battery which is there within the vehicle, as well as the charging infrastructure which is available to charge. Having said that, my dear friends, it's one point should be very clearly memorized, that we cannot uh, go to any charging panel and get it charged. For example, if the capacity of the battery is, let's say, the maximum capacity of a battery which can at a single point of time get connected to a particular charger, if that is limited up to 60 kilowatt, and then you cannot go to a charging panel or capacity of 100 kilowatt or 200 kilowatt, then you're blocking that particular charger for the time which otherwise would have been taken up by some other higher capacity vehicle. So the capacity of a charging panel at the max is limited to the capacity how much the battery can hold, right? So this is the point. So now let's walk through this slide, which speaks about the different battery chemistry. So lead acid battery, quite commonly seen and very popular one, which is widely used in our UPS applications. And conventionally, this is the only battery from childhood we know, right? All of us are very familiar about this battery type. So the challenge is this maintenance and acid leaking and the chemical pollutions and all the hazards and maintenance issue is the biggest challenge here, adding distilled water on frequent basis and all this stuff. And apart from this carries a huge volume of space. I mean, this is quite like a bringing elephant into the home, right? It occupies unnecessary space and volume, and then and also subjected to the change in chemistry with the temperature variations, atmospheric dependent battery. The main advantage with this lead acid battery, the reason why it is still surviving in the market till date is that it's quite cheaper, right, compared to any other battery chemistry type. So that is the main reason why it is surviving, especially for a country like India, where we first see the economics and then see the technology. So for us, lead acid battery is like a long old friend. We cannot give him up, right? And the nickel cadmium battery is another type. So compared to lead acid battery, there is a technical merit. So in this particular battery chemistry, so good performance at low temperature, good life cycle at low temperature, holds charge when not in use, and all this stuff. But it also suffers from one typical demerit that is called as dreaded memory effect. So if you just closely look into this aspect, so let's say if this particular battery chemistry is continuously being discharged up to 50% of its state of charge limits, then eventually this nickel cadmium would forget its capability that otherwise would have been discharged till 20% or 10%. So a kind of virtual blocking is there, which is stopping you to discharge the battery beyond this memory effect. So, but still it finds applications in toys, aircrafts, and electric vehicles as well. And then nickel metal hydride, which has higher capacity and energy density as twice as that of compared to nickel cadmium, and used for consumers, electronics, and electric vehicles. But seriously, a particular battery which all of us like a most, like this is like an iPhone in the chemistry, in the battery chemistry. What is that? It's a lithium ion, right? So it's a high energy density device, very compact, occupies less volume, and wide range of temperature operations, low self discharge, no dreaded memory effect, wide variety of applications like aerospace, military. Uh, you name a guy who don't like lithium ion, nobody, you don't find anyone hardly, right? So, but the only challenge with the lithium chemistry is this high cost, right? It's a high cost. Now let's see, assuming that we are going to use lithium ion alone for meeting out the expectations, as I've already indicated in the beginning of my talk, that we have a gigantic plan of going forward to install 500 gigawatt of renewables by 2030, including solar photovoltaics and the wind plants, and replacing all the vehicles, mobile vehicles, with the EVs. So what is the kind of battery requirement that we have? So it's around 3,500 gigawatt hour by 2030. So in different phases. So and that adds on to a economic value of 150,000 million US dollars. 150,000 million US dollars is a huge number. So let's see where we stand today. The biggest problem, my dear friends, is if you have such an ambitious goal, then we need to look into the ground reality. The ground reality is we don't have lithium resources today. It's again another problem like a thorium, right? So we don't have uranium, and thorium is not evolved much. So that's why nuclear power plants are not so significant in this country. So, but it's a kind of a similar problem. Battery is inevitable, but unfortunately, lithium is not available. Not only lithium resources, we don't have even cell manufacturing units. Probably we have cell assembling units. What we usually do, and I've also been collaborated um, uh, with uh, with many companies, and one of those companies is located in Kanpur. What they do is they purchase cells from China and they bring here and assemble and then market it. So this is a basic formula that everybody follows. So we don't have cell manufacturing unit, my dear friends. So we are dependent upon other countries. So this is another challenge, infrastructure. So what are the alternate options that we have today? So Redux is a good option. Long life, safer, fast response, recommended for renewable applications. demerit is low energy density, and sometimes if you have a good space, you don't have to worry about that. And then the sodium based batteries and lithium sulfur batteries are another options. Especially I'll just focus on the sodium batteries. The reason being, we have good resources, being India being a subcontinent covered 3 sides by the saline water. So this sodium is easily extractable, even Mahatma Gandhiji also has taught us how to get our own salt out of the sea. The salt and the sodium is readily available with us. So this is a major advantage we have here. So factors affecting charging. So battery size is one such. If battery size is higher, then longer it would take to charge. And the state of charge, like if you're starting from 50% or 80%, naturally there is a difference in time. And then maximum charging rate of vehicles. As I've already mentioned this point, if the vehicle charge rate is 7 kilowatt, then it's not possible to use a 22 kilowatt charging point. Even though you plug in your vehicle to a 22 kilowatt charge point, the capacity is only limited up to 7 kilowatt here. And maximum charging rate of charge point and the environmental factors like varying temperatures is another reason why it would hamper or disturb the charging capacity. And then time of a day, more electric vehicles in rush, and type of charging cable that you use, whether it's a type 1, type 2, CADIMO, whatever capacity of the cable that you use in, and then battery drain out or idling, keeping battery dead for a long time. All these things affect lifestyle of a battery and indirectly has an effect on charging capacity as well. So how do you charge your vehicle? So there are 4 ways of doing it as I see in the literature. One is onboard charging, right? So you go to a charging station and plug in and then charge, or you plug in to your home and then charge. And solar power based EV stations, which is quite commonly seen in many companies and malls where they cover this parking slot with the panels. There is a dual advantage. You also get a shelter for the vehicle and as well as use the space for the charging vehicles. And then the wireless charging is also another area where research scholars or researchers are eagerly working. One of my colleagues also in Kanpur is developing chargers, and many startups are also there in Kanpur as well working on this area. And road constructed for dynamic charging. This is one such thing which attracted me because here you don't have to wait. I think one such pilot being established in Europe, I guess. So it's like you have different lanes, and one such lane is a green lane. So you keep moving on through this lane, and then vehicle being charged. So you don't have to wait here. So there is an off-board charger in a vehicle and an on-board charger. So if you're going to a charging station, then probably you use the off-board charger, and you're using the electricity at your home for charging your vehicle. Probably you use the on-board charger. And different types of converters used for charging. I've just listed the typical topologies which all of us are quite familiar about. So if full bridge, diode bridge rectifier, boost converter, buck boost converter, or bidirectional converters if you want to go for V2G or G2V kind of applications. And if you want to connect to a AC system, then it's DC to AC H bridge. Here I've given a topology of full H bridge inverter. Or you can go for a dual active bridge if you need an isolation between a charger and the battery, and then the flyback and forward and push pull and all these isolated types of topologies. The advantage of this topologies is that the faults can be isolated, and then you can also bring in the factor of safety and grounding issues also here. So given this background of EV, now let's jump into the impact of these EVs on the power system, right? So various challenges that we can think of. So primarily it's a power quality issue because you use converters and you connect to charging stations. Let's say number is not so high now, but when we speak about volumes of hundreds and thousands of electric vehicles plugging in directly to the charging infrastructures, and a lot of converters injecting harmonics, so may pollute our grid. impact on voltage stability. So naturally, if a particular feeder is carrying a lot of vehicles, so at a particular time there could be stability issues. Impact on transformer life. The conventional age-old transformers are not meant to accommodate the electric vehicles. So this is a new technology which is pumping in. So the transformers efficiency and life may also get degraded. Impact of EV charging stations, stability of power grid. Here the stability which I speak is about synchronous machine stability, impact on supply and demand balance of power grid, impact of current harmonics on utility grid, impact on environment, and all this stuff need to be taken into consideration. So the power quality issues, I'll just discuss three of them in a brief. The first one is the power quality of the distribution system. These are the typical power quality issues that we all familiar about: transients and the harmonics, the reactive power, the network unbalance, oscillations, voltage variations, flicker. We all see this in day-to-day life, right? Probably nowadays the flicker issue is not so significant. At least during my childhood, I recall when I used to study, the bulb used to flicker a lot, especially in the rural grids. I don't know whether that still persists or not. And there used to be a lot of unscheduled power cuts. So we are doing good gradually, because I see many villages are being powered up, but not all of them. I had a survey in Uttar Pradesh, got an opportunity to interact with many villagers. I personally went to remote villages of this state, and I could see what you know this power for all, and we have reached out to the remote villages, and all this stuff is fantastic. But ultimately, the ground reality is that the villagers are still struggling hard to get a reliable, good power quality supply. Hardly 4 hours or 6 hours per day that they do get electricity, and that too the voltage is quite fluctuating actually. So this is a kind of situation where we are in. For the namesake, as a part of political agenda, they claim that we have given electricities to all of us, but the ground reality of good quality power supply, which is a basic necessity of a humanity, is still mm, still not achieved at many places. Okay, large scale EV charging causes under voltage conditions, power imbalances, voltage and current harmonics. Heavy voltage drop due to EV charging may cause frequent switching of the voltage, leading to its life degradation. This is an important issue. Many of the countries today are speaking about solid state transformers, SST. So if you have a SST in the system, probably you're not worried much about the tap changing issues. But today in this country, we do possess only mechanical based on-load tap changing transformers, which has a limited operations of up to 10 to 12 operations probably per year. So if you have these EV charging stations connected to these feeders where this OLTC is connected at the substations, so naturally if frequent tap changing is expected, because as a basic concern, the OLTC is designed for this purpose to maintain nominal voltage of 1 per unit at the bus where it is connected. So most of the bus are still radial network is seen. So naturally there is frequent OLTC tap changing, and that will degrade the life of OLTC as well. So the increased load due to simultaneous EV charging would cause additional voltage drops, affecting the service voltage quality. By proper charging algorithms and knowing unbalance in a particular phase, the EV can also be used to mitigate this issue. This is an interesting point. The first 3 points indicate the negative impact of EV on the distribution system. At the last, probably I would have highlighted in a different color. This indicates if a particular EV, which is creating so much of trouble to charging stations through charging station on a power system network, if those EVs are properly managed, then already existing unbalance in the distribution system, which is a major issue, can be solved, right? So like if the two phases are carrying higher current, the third phase is carrying lower current, and probably you can bring in your vehicles, ask the vehicles to come and plug into this to the third phase and try to balance this current across these three phases. impact of EV being continued. So transformers being overheated and overloaded, and capacity power cables also I square R losses will increase because of higher load, additional load being added because of this presence of electric vehicles in the system. And the capacitors, already there are shunt capacitors which are present um, to maintain the voltage stability. And then there could be resonance because of switching, and then inductors are being placed. It's a non-linear load anyway, so there could be some resonance, and some stability issues may also pop in there. And then protection also may get hampered because of so many EVs and bidirectional power flow. So protection issues may also there. Professor Abhijit here is also working in this direction, and so many faculties across the country are also working on in this area. I guess Professor Vishal is also working in this protection aspect. Other power quality issues include phantom loading, right? So connect some charging stations will draw some power even if there is no load being connected. So it's a power loss anyway. And load unbalance, which I've already discussed, and DC offset due to harmonics. So this is an interesting case study from California. You see is a load curve being plotted for the 24 hours. You see there is a valley and then there is a peak. So this peak is happening during the late evening hours because that's the time when the vehicles would come back and then gets charged, right? But the unfortunate story is, and the most painful story for a power engineer is that the solar is um, available only during the daytime, right? The peak of a solar can be seen on the noon, where the total load on the grid is very less. So henceforth, you need additional battery there, right? So usually the ideal case would be that we neither want a valley nor want a peak, we want a flat curve. So that's the ideal thing. You can see here with the number of vehicles being increased up to 6 million, the red spots are quite high. That indicates that there is more overloading on the existing feeders. And the Maldives case study also indicates the same thing. The peak demand shoots up as the number of vehicles increases. So that's the background of EV and its impact on the power system grid. I'll discuss about the case studies of EVs and renewables towards the end. Now let's jump into the renewables part of today's discussions. So this is a pretty old data. So currently we may have around 240 or gigawatt around of renewables. Okay. Photovoltaics, this fundamental physics, you all know that packets of energy in the form of photons being absorbed, and that helps to move electron from valence band to the conduction band, passing through this band gap. All this stuff, this stuff. So this is a PV cell model, single cell, single diode equivalent circuit of a photovoltaic cell. So you have two resistors here, right? RP and RS. What do they indicate? So RS is a series resistor we connect usually to a voltage source, right? So that means we are trying to say that some portion of the IV characteristics of a cell will also behave like a voltage source. And RP is a shunt resistor which is connected across this current source because it indicates the current source. And mostly we see in the IV characteristics that I'll show you in the next slide will behave like constant current source. So henceforth we also say if there is any current source which is practically available, and that we call it as a photovoltaics, right? Mostly it is RP dominated and then less dominated by RS. So we use this diode also to obtain this IV characteristics. So these are the fundamental equations. This is the IV characteristics of photovoltaics, as you can see here. So there are three operating points, major operating points as such. One is short circuit current point where the voltage is zero, hence the power is zero, and the open circuit voltage point where the current is zero and hence the power is zero. So the most interesting operating point or most um, popular operating point is this MPP point. the current is neither maximum or voltage is maximum, but the product of current and voltage is maximum, right? So that's what the PV curve also indicates. So this is a typical layout. You have a PV source, then there is a load. In between, you need power interface or a converter. Why do we need it? Because PV source has its own internal impedance, load has its own impedance, and we know that maximum power can be transferred if the impedance matches. So impedance matching is done with the help of this power interface or a converter, for which it's a muzzle. The switches are the muzzle, switches and inductors and all these cables are the muzzle of this power interface, and the brain is this controller which receives inputs from various atmospheric conditions like temperature, irradiation, and the sense parameters like voltage, current at the input and output side. So in the photovoltaics, you have various types of panels, and I don't have time to discuss all of them. Typically monocrystalline, poly, and thin film. The power interface, which we have already covered for the EV side, is also applicable here. Buck boost, and buck converters, depending upon the voltage level that you need to operate. So, and the kind of panels that you plug in. So you choose any type of converter, and don't get confused. Often I see students would say MPPT is only possible through boost converters, sir. So that's not the case. MPPT is possible either through any of these converters. Only thing is, you choose a converter based on the operating voltage limits, right? So, and the controller is MPPT controller or inverter controller. The load could be a resistive load, battery, grid feeding, AC loads, and all this stuff could be isolated or a grid connected mode of operations. So what is the operating point? The operating point is that point which intersects the load line with the line of the characteristics of a source, right? Be it could be electrical machines or the photovoltaics. This is a universal formula, right? So this is a IV characteristics of a particular PV panel, and this, let's say this is a load line. So load line is meeting this IV characteristics at this point, and henceforth this is operating point. But the MPPT point is somewhere here. So if you operate, you're forced to operate here, but the point is you don't want to operate here. You want somewhere here, but you cannot change the load line. To change the load line, you have to change the load. So nobody wants to change the load, right? So let's keep the load line as it is, but how do we extract maximum power in spite of load line being connected here is what these converters would do. So in the short circuit point, we have R naught is equal to 0. And at the open circuit point, we have R naught is equal to infinity. So the power lost because of not operating in MPPT point is this much, the red color one. And the maximum power point tracking is done by changing the operating point with the help of this power interface, which is a converter, right? So you move this converter and relocate it, move this operating point and relocate it at the MPP point. So to do this, you need different types of converter topology. So let's discuss about the boost converter. You see here, this is voltage equations. V naught is equal to VPV by 1 minus D. Current equations is I naught is equal to IPV into 1 minus D, which we are all familiar about. And obtain the resistance equations, which is R naught is equal to RPV by 1 minus D whole square. And this is the maximum range of operation. D is equal to 0 to D is equal to 1. D is a duty here. So if duty is 1, that means you always turn on the switch. So in that case, the RPV is equal to 0. Duty is equal to 1. That means R naught into 0. Then RPV is equal to 0. That means this indicates a short circuit point. It's a short circuit point. And if D is equal to 0, and then that indicates a load line limit R naught. So with the help of boost converter, either you operate, the boundaries are limited between the short circuit point and the load line. So let's say this load line is above the MPPT point somewhere here, then no matter what kind of duty you operate in, then you will never be able to meet this point, MPPT point, because it's hard limited to the boundary created by this load line. If load line is below this MPP point, and then you can track the MPPT by changing the duty. Similarly, for the buck converter as well, you get exactly opposite as you operating range as compared to the boost converter. So here the load line lies between the open circuit point and the load line. The operating range is between the load line and the open circuit point. So henceforth, if the load line lies below this MPP point, in this case, you will never be able to track the MPPT. Rather, you always want this load line to be above this MPP point to track the MPPT, unlike the other case where we discussed with the help of boost converter. So these are the fundamental equations which I guess you are all familiar about it. And then the buck boost converter, where you get the complete horizon of the IV characteristics can be explored to track the MPP point in spite of the load line. So here the load line doesn't bring a constraint to put a boundary limits. Rather, the short circuit point and the open circuit voltage point are those lines which keep the bound, which limits the operating range, and that fairly indicates that PV MPPT is quite possible in the case of buck boost converter in spite of the load line characteristics. And various MPP methods which are quite commonly engaged, like the most important one is the perturb and observe method. So as you can rightly see, you're climbing the hill here. I've just drawn a power versus voltage characteristics. You're climbing the hill and then reaching the peak point. And then you perturb and see the observation. If whatever the perturbation that you have done, if it is bringing a positive response, then you continue to create the same kind of perturbations in the similar direction and reach the maximum power point. That's the objective. And at this particular perturbation, the power has decreased, so you're coming back again. And then this is the finalized operating point here. So this is the overall algorithm that you can see here, a flowchart which is used for the MPPT tracking. So in real time, you measure the voltage based on the sample time. You measure the power, which is instantaneous voltage and current multiplication. See the change in voltage and change in the power. Change in power and the change in voltage. Based on this, there are 4 different operating range that is possible. Other divisions can be made where you can track the MPPT. So if power is 0 and power is less than 0, so if power is 0, you stop the MPPT tracking, the change in power. Or if change in power is negative, then you check whether the change in voltage is negative or not. And if it is negative, then you increase the voltage reference by increasing the duty. And similarly, you can track this various operating range and then take a call. So this is particle swarm optimization. So why do we use this? It's a heuristic approach. If you have multiple peaks because of shading, so then this methodology is used to obtain the global peak. Right. So this is a background of photovoltaics. Now I'll discuss about the wind energy conversion system. So the statistics suggest that even if 1% of the wind energy is effectively utilized, available wind energy, then it can satisfy the global power demand. So such is a potential of wind energy also. Often we just focus only on solar photovoltaics, but to be very honest, wind energy has a huge potential. But the unfortunate situation is that, because of difficulties in reaching out to different hilly areas, there is a limited wind power plants that are currently being deployed. But people are also looking forward to extract the available wind in the on the sea, which we call it as offshore wind plants. So these are the typical wind turbines which are used: horizontal axis and the vertical axis. So the horizontal axis, the axis of hub rotation is parallel to the ground, whereas in the vertical axis, the axis of hub rotation is perpendicular to the ground. So you can just imagine this. So mostly the horizontal axis turbine are used because of its higher power extracting capacities. So these are the typical components of a wind power plants that you can see. This is a foundation, civil foundation, and then you have cable outlet which is connected accessor the point of common coupling where you connect the generator outlet to the grid, and then you have a staircase which is meant for maintenance purpose, and then you have a vertical structure to raise the tower such that you can capture the high wind flowing uh, through a higher vertical distance. And then the important point aspect of this slide is discussed through this portion of the wind power plant. So which includes the hub, which houses for the gearbox and the generator. And you also have a hub, which effectively helps to convert wind energy into mechanical energy. And then the blades which will rotate the hub basically, right? So why do you need the gearbox? The gearbox is necessary. The reason being, uh, the whole hub is rotating at a very low speed. You might have also seen in while you're traveling through trains, there could be some visible wind power turbines, wind plants, where the blade is rotating very slowly. Though the blade is rotating very slowly, you may be thinking, probably there is no generation happening, but internally there is a conversion, mechanical conversion, through which there is good rotating speed available next to the generator, and through which electricity is produced, right? So this is overall schematic of a wind energy conversion system. You have a kinetic energy flowing from wind and being applied on the wind blades, and then the wind turbine rotates. It's coupled with the gearbox, where you convert high torque rotating mass to a low torque rotating mass, or from low speed to high speed, and which is again coupled with the generator. So typical type of generators which are commonly used are induction machine and a synchronous machine, which I'll discuss in the further slides. And still you process it through the power converters and add some filters and eventually make it feasible to get connected to the grid. So this is a power versus wind speed characteristic. See, there are three different instances which is of high importance. One is cut-in speed. Cut-in speed is that speed where there is some significant amount of power production is possible. Below this cut-in speed also there could be electricity generation possible, but that is mostly swallowed by its own losses. So mostly we don't recommend to operate at any speed less than this cut-in speed of that particular site. And then the relationship is highly nonlinear between cut-in speed to rated speed. So that expression is given here. Power output is given by Cp, which is a function of lambda and beta, where lambda is called as pitch angle. Lambda is called as tip speed ratio, and beta is called as pitch angle. Into rho is a air density, area of a blade, and then V wind is the wind velocity. So V wind cube. So the relationship is mostly cubical relationship. Henceforth, you see this kind of curve. And then once you reach the rated speed at which you generate the rated power, then more or less the power output, power generated from the wind turbine is constant in spite of the speed of the wind increases, wind velocity increases. Till that point, you keep on operating this wind turbine, which is called as a cutout speed. This is a very dangerously high wind speed, which is not recommended to be applied to the wind turbines, right? So usually we try to disorient our turbines such that we reduce the high impact force on the turbine and try to safeguard the plant basically. So cutoff speed, after cutoff speed, there's no power generation. And these characteristics are also quite important. So this is a turbine power output versus turbine speed, right? So it depends upon two factors mainly. One is the blade pitch angle, and then the turbine speed. Of course, it is the power output changes with respect to the turbine speed, and the wind velocity is also another reason why the power output increases, right? So as you can rightly see, if the wind velocity increases, you get a higher volume of power being generated from the same wind turbine. So the interesting observation that you can all make is this, that if you keep the pitch angle equal to 0, then whatever amount of power you generate for the same wind velocity, and if you increase the pitch angle to 1 degree, so you reduce the power output for the same wind velocity for the same turbine. So hence pitch angles control um, of speed variations or power output variation is mostly applied for the cases where there's a high gush of wind speed and you want to take away the power output or reduce the power output from the particular wind turbine. So this is mostly used for high speeds, and the turbine speed variation of power output control is mostly employed for the low speed wind variations. So typically there are three types of controllers being engaged to change the power output of a wind turbine. One is called as a pitch angle control, as I've already discussed. So this is a picture which will help you to understand that the blades are connected to this hub, and you change the blade positions such that the angle of attack can be changed, and then the power output from the turbine will also reduce. And then there is a yaw control where you change the whole vertical portion of the wind turbine, and that will eventually change the position of the entire turbine being exposed to the wind velocity. Yaw control mechanism is mostly employed for those scenarios where there is a change in the wind velocity altogether. Based on your case studies for entire year, you probably might have placed this um, uh, this uh, this entire turbine facing a particular direction. But eventually, if wind direction changes, then you have to disorient the turbine such that you allow this blade to absorb maximum kinetic energy flowing through the wind. And then the rotor speed control, so which I've already discussed, is mainly employed for those operating range where the turbine speeds are less and you can extract maximum power out of it. So these are typical types of wind generators being employed. The type 1, type 2, type 3, type 4, type 5 generators. In the type 1 generator, we use squirrel cage types of machines connected to the power compensators, bypass switch, and through the step-up transformer being fed to the grid. So the basics of induction machines were really help us to understand that squirrel cage induction machine is not much favorable if you want to access the power control through the rotor side, because the rotor is short circuited here. So henceforth, it's a unidirectional power flow that is happening here, and not much speed variations or rotor speed variations or the power output variations are possible here in this particular case, unless you go for a pitch angle control mechanism, which is usually done for higher speeds, as I've already indicated. So not much speed variations or power output variations possible through this type 1 generators. Whereas type 2 generator, though you're going for a wound rotor mechanisms, but you're going for a physical resistor, mechanical resistor. I mean, the point is you're going to use a physical resistor and a mechanical means of changing this resistance values. So though there is an accessibility at the rotor side, but not much speed variation is possible here. But the W-fed induction generator is what is the most popularly adopted. Even the biggest manufacturers like Suzlon, if you go to their portal and observe, they have a typical turbines of 2.1 megawatt capacity where they use this W-fed induction generator types. And across the mostly in China, we go for type 4 or type 5 because there is a lot of permanent magnet resources available freely there. But in the country like India, again, another problem of resources. One problem of resources that we have covered in today's discussion is the lithium ion, right? Which is mostly seen in the China. So here also the permanent magnets are not seen in this country. So the resources are not available in this country. So we are dependent on the neighbor country as well. So henceforth type 4 is not so well accommodated in this country. So type 3 is a very popular one. The why I call it as popular, because the speed variation is very much connected to the practical reality. So most of the wind turbines that we see being installed across the country requires the speed variations around plus or minus 30%. the wind speed varies within the range of plus or minus that, I mean, eventually leading to a power variations of plus or minus 30%. Henceforth, you can use a partial rated converters at the rotor side, which can help you to extract maximum power or control the reactive power flow, or to help you to sustain through the fault rate through behavior. So it makes this entire topology interesting topology, both from the technical side and the economic side. From the economic side, the reason being the partial rated converters which are employed, so make it more economical. And from the technical point of view, as I already mentioned, it really help you to control the speed or power output in a very good range, where most of the wind turbine speed variations are seen in the range of plus or minus 30%. So nothing much that you're going to lose. That's the point we are trying to make here, as compared to the type 4 generators. So what is this type 4 generators? Here you're going to go for a full rated capacity of power electronics converters, because the stator output, there is a wind turbine which is connected to the gearbox, and the gearbox is coupled with the rotor of a generator. Let's say you're going for a permanent magnet machine here. So the permanent magnet output, no matter the cutting speed is as low as 2 meters per second, 3 meters per second, it doesn't matter. So whatever is the power output, if it is some significant value, so you convert it into DC, AC to DC, and then from DC to AC, and whatever is, let's say even few amps of current can also be fed to the grid, theoretically saying. So, the point is, economics is quite concerned, because you're going to go for a full rated capacity of converters. On the other hand, there is a technical merit also, because you're hiding your machine from the grid. So whatever the dynamics that you see at the grid is not directly implicated upon your machine. Whereas in the case of type 3 generator, so the dynamics of a machine is freely seen or directly perceived from the machine side also. Because the stator is directly exposed to the grid or connected to the grid. So if there is a fault or a disturbance or unbalance being seen on the grid side, so that you see also being reflected directly upon the machine side as well. So that is a vital problem that we face through the W-fed induction generator, which we call it as a fault rate through performance. And many research works have been carried out to solve this issue, both from the hardware and the software side as well. If time permits, we'll discuss a couple of the case studies in today's discussion also. So this is a W-fed induction generator. So I'll just give you a generalized understanding of how the system works. So let's say it's a 6-pole induction machine, slip ring induction machine being employed, and the synchronous speed of operation is 1000 RPM. So then if the speed variation, wind speed is such that the speed has not reached the 1000 RPM, which is a synchronous speed, ideally at which you generate the power at 50 Hertz and can be synchronized with the grid. The rotor speed is much lesser, maybe it is 800 or 900 RPM. So there is a positive slip. Slip could be 0.1 or 0.2 or whatever. So in that case, you need some power from the rotor side, some assistance from the rotor side, so that you make it look like a 50 Hertz power and then feed it to the grid. Because the point is, to synchronize your stator to the grid, you need to maintain these fundamental rules that, voltage should be same, phase angle should be same, frequency should match, and all this stuff. So you need to match the frequency at any cost. You cannot say that, I cannot do anything because the rotor speed is less and I generate only at 48 Hertz or 45 Hertz. That is not possible. You need to make it 50 Hertz to go to, go and get connected to the grid. So that adjustment of power is being done through this rotor side converter, my dear friends, which will borrow power from its neighbor, which is a DC link capacitor. So the DC link capacitor in itself is not an energy source. It's just a temporary energy storing element which can maintain the voltage at a certain level. So if you take out active power from this DC link capacitor, there is a dip in voltage, right? So this dip in voltage need to be maintained by this another converter, which is called as a grid side converter. And how does it do? So it would carry power from the point of common coupling and try to maintain this DC link voltage constant, and then ensure that the lack of power which was expected at the machine side being taken back from the same point of common coupling indirectly. So on the other hand, if the speed due to some reasons, if wind speed increases and the rotor speed shoots up beyond the synchronous speed of a machine, then what happens? So there is a 50 hertz component which will be directly flowing through the grid, and there is an excess component of energy also being also seen at the stator side. So that need to be evacuated through some other direction or some other channel, and that channel is this rotor side. So here in this particular case, the power flows from the machine to the rotor side converter, and rotor side converter will dump this power on the DC link capacitor, because of which the DC link capacitor voltage shoots up. You need to maintain this voltage at the nominal value so that you observe this transient and feed it to the grid. So in either way, whether the speed is less or high than the synchronous speed, this machine is comfortably working synchronized with the grid, and there is another channel of power flow which is being established through the rotor side, which is well connected and controlled through the back-to-back converters, just to ensure that the speed variations are comfortably allowed in this particular kind of machine. So this is a whole philosophy of how W-fed induction generator works. So whatever I've told is what is displayed through various control schemes in this particular slide. So as you can see, you sense the signals and then convert from ABC to DQ frame. The objective of rotor side converter, my dear friends, is to extract maximum power from the turbine. I'll explain how do we do it. And then another objective of rotor side converter, because there are 2 degrees of freedom, D control and Q control, both available for the rotor side converter and the grid side converter. So with the help of D control, we adjust the power factor or try to inject the reactive power. And with the help of Q control, we track the MPPT here. In the case of grid side converter control, with the help of D axis, we change the power, we adjust the active power. And then with the help of Q control, we do the reactive power management in the case of grid side converter. So how do we do the MPPT tracking is what important. Please understand that power output is a multiplication of electromagnetic power so what is that? Electromagnetic torque and the speed, right? So the torque is dependent upon flux and the current. Flux is what is the stator voltage. So you cannot change the flux. Flux is fixed. You change the current, you change the torque. You change the torque, you indirectly change the speed. So that's what we are trying to say here. So as we have already seen the characteristics, if power changes based on the rotor speed, and the rotor speed is adjusted as you inject the current. So because the torque changes in the end and there's impact on the speed. So for each particular turbine at a particular velocity, there is an ideal optimum speed that you want to track. If you track that speed, and then the whole job is done, you're tracking the MPPT. And how do you track the speed? By adjusting the current. So in that, then how do you change the current? By changing the switching pulses of this rotor side converter, because the current output of this machine changes when you change because it's simple KCL. So there is a current input also coming from the rotor side converter. So you change this input, and then eventually there is summing up current also changes. So that's how rotor side converter is helping us to change the operating point and to ensure that you track the maximum power point. This is also kind of a perturb and observe method only. So in addition to the rotor speed control, there is also pitch angle control mechanism, which will try to adjust the blade position in such a way that you change the power output from the turbine, which I've already covered in the previous slides. So this is a closed loop control mechanism where for the grid side converter operation, where you sense the actual voltage and there is a reference voltage, and then the difference in current will further trigger another PI control loop, and then you track this current in such a way that you maintain this DC link voltage constant. So some of the research areas or topics of W-fed induction generator, the fault rate through, the balance, and for the unbalanced fault. In the case of fault rate through scenarios, what usually happens is, let's say there is a dip in voltage, because when there is a fault, so naturally there is a dip in voltage because huge current flowing and there is a dip in voltage. And then if there is a dip in voltage, the flux is a state variable in this machine, right? So flux is not allowed to change suddenly. So if there is a dip in voltage, there is a bondage between flux and the voltage. The voltage changes, but flux will not change. So there is a kind of transient response being offered from the flux side, and that transient response is that a DC component of flux being imposed. Now, please understand, in steady state operation, the flux which is present is synchronized with the time variation as of the voltage. So it's a time varying flux, right? There is no DC there. So the rotor is rotating close to synchronous speed, and the relative speed variation is very less. So the voltage being induced on the rotor side is very minimal. Whereas whenever there is a transient event, there is a DC component of flux which is also seen in addition to the AC component of flux, which is steady state. So there is a DC on the stator now, and there is a rotating rotor which is rotating at a synchronous speed. So the relative speed variation is quite high, and because of flux cutting principle, and there is a dynamically induced EMF of a high magnitude seen on the rotor side, and that will induce a huge current flowing through the switches, and because of which the switches may blow off, because the converters are meant to carry only 30% of its capacity as compared to the stator side. But in this particular situation, for a transient duration, maybe for 180 milliseconds, 200 milliseconds, or depends upon the grid codes. The German grid code suggests at least for 150 or 180 milliseconds, you need to get connected to the grid, even during the case of zero voltage right through, dead short circuit. So that's a huge severe implication, or a kind of damage being imposed on the machine side, on the converter side. So rotor speed increases because there is no way out where you can pump in the power. Huge accumulation, huge speed being seen on the rotor side. And then there is DC link capacitor which may also get damaged. So this is a challenge. And then there is inertia control, because this is an important research topic again. So most often we speak about the inertia challenge because the converters that we have today, they don't offer inertia, right? The synchronous machines have a natural inertial component, but we don't have inertia offering through these converters. So you need to offer a kind of virtual inertia. That is one option. Or let's say you are going for a renewable, like W-fed induction machine, where there is also inertia component which is directly seen, because the rotor is there and stator is directly connected to the grid. So W-fed induction machine is one such machine which can closely help us to feel the presence of a synchronous machine. So henceforth, inertia control mechanism through the W-fed induction machine is also a good research problem to think of. And then the power quality, because of this converters anyway, there is a power quality issue. So, and then the voltage control of the network, cost-effective hybrid system in architecture. Why do you need a cost-effective hybrid system architecture? Because when you bring in solar photovoltaics and wind, both of them are complementary to each other. So you can decide what best architecture that can be employed, so that you can share the components with one another and try to bring out the economical merits as well. And loss minimization also by effective reactive power management, isolated power feeding to the DC grid. So which is a famous research problem being worked out from the European countries, not much being studied from the Asian countries. So many research articles of how we can use the W-fed induction machine for a isolated DC microgrid application, which I don't want to discuss because of lack of time. And then the wake effect also, which I'll cover towards the end. And then the HVDC power transmission in offshore wind farms and fault analysis, which is also a very interesting research problem, because you go for HVDC application, there could be stability issues because of the long distance and the fault, because the cable is going through the underwater. So there could be some fault studies also being carried out. Sensorless speed control, maximum power point tracking. Sensorless speed control is also a good research problem where you find a lot of research papers seen. You can avoid the sensors and try to control the speed. So that is also there. And maximum power point tracking with various heuristic approaches or the conventional techniques also seen. So this LVRT codes I've already discussed. I'll skip these slides. The solutions for the LVRT, like hardware solutions and software methods. So in the hardware, you have crowbar protection, where you uh, actually short circuit the rotor during the fault and try to protect the converters. But the challenge is the machine will now behave like an induction motor. So there are two expectations from a double-fed induction machine or any inverter whose capacity, if it is more than 5 megawatt, as I remember, IEEE 1547 standards clearly indicate that the renewable power plant should get connected during the time of faults and also support the grid by injecting the reactive power. So if you go for crowbar protection, no doubt you're doing the first job perfectly, where you're connected to the system and you're protecting your machine also. The first expectation is satisfied, but the second most important expectation is the reactive power injection to the grid. So here what is happening? There is a reactive power consumption going on, because induction motor will draw reactive power. Already the grid is suffering because of lack of reactive power, and then now we are adding uh, more challenges to the existing challenge. So the crowbar is now, it's a very old technique and not employed now. And we go for DC chopper, where we connect a switch and a resistor combination in at the DC link side. And if there is a shoot up in the DC link voltage, you bypass this. You basically discharge through the resistor by turning on the switch. So the DC chopper is also used. And then we go for dynamic voltage restorer. So here we use an inverter and a transformer at the point of common coupling, and then in addition to the DFIG machine. So the root cause of all this problem is the dip in voltage, right? Through the support of DVR, we try to restore the voltage so that the entire problem is solved. But this brings in the additional cost. And DStatCom also meant to support the reactive power requirement during the kind of fault situations. And the fault current limiter also is used, where it tries to reduce the impact of fault on the double-fed induction machine. Indirectly, it tries to reduce the dip in voltage so that you solve the problem partially at least. So these are the hardware solutions, and many such solutions are seen in the literature, but I'm not discussing them. And then the software approach indicates you basically uh, offer a compensation flux. Uh, what is happening is there is a magnetizing component of flux being produced during the fault, right? And that is the reason why you're generating the voltage. There is more voltage being seen on the rotor side. So you produce a counter flux with the help of rotor side converter or grid side converter, and try to kill the magnetizing fields, actually. Magnetizing flux. And that's how you do it. And the flux picking is also similar approach. So these are the software approach, which is also seen here in the literature. So large wind farms, all this stuff. I'll skip these slides, we have already covered. So different energy storage technologies for renewables. We have discussed energy storage technologies, especially the battery chemistry type for the electric vehicle application. And similarly, you need different combination of storage technologies for the renewables as well, right? Because renewables are available during a specific time, and you need to have continuous energy flow 24/7. So how do you match it? With the help of storage technology. In the mechanical types, you have a pumped hydro storage, energy storage. So most of our transmission grid, we use this pumped hydro energy storage, right? So what it does, so there is a upper reservoir and a lower reservoir. So during the peak hour, you store the water from the lower reservoir. So you use the water from the higher reservoir to generate the electricity and feed it to the grid. And during the off-peak hours, so water is there in the lower basin, and you pump it to the upper reservoir and store it so that you can use it for next peak hour. So the efficiency is also quite good, pretty good. In fact, I guess it's around 72% round the trip. So so pumped hydro or flywheel energy storage is also a kind of mechanical storage that is used. And you store the energy in the form of a huge rotating inertia mass, and then release it whenever you require. And then compressed air energy storage also, you compress the air, and high power density is being created, and then you use it for power generation laterwards. And then in the electrochemical, you have a chemistry type like lead acid battery, lithium ion, redox sodium batteries, zinc batteries, um, many types of chemistry types in the electrochemical type. And then the thermal storage, where you use glycogen or some kind of metal, which some kind of liquid which is used to circulate and store the energy basically. In IIT Kanpur, we have thermal storage system, which is helping us to reduce the chiller loads. And then there is electricity based storage types, so like supercapacitor, superconductive magnetic energy storage, which is used. And then hydrogen, of course, is picking up uh, quite aggressively. So uh, you use the electrolyzer, and then from renewable you convert it and store hydrogen in the tanks. And then when you want to generate the electricity, then use the hydrogen through fuel cell and then generate the electricity. So the challenge with this hydrogen technology is that the efficiency is quite low, maybe around 40% or less as compared to the pumped hydro storage. Um, Of course, but country and the whole world is looking forward to improve the efficiency and make it more technically feasible to deploy it across various applications. And then gravity storage type, where you have pumped hydro. It's a kind of a pumped hydro storage only, rather than using pumped hydro. The hydro as a medium through which you store the energy. Here you use different mechanisms like sand or solid blocks, so to use the gravitational potential to harness or store the energy basically. So moving forward, we discussed about EV impact on the grid, on the power system, and similarly there is a renewable penetration impact also on the power system, like origin of harmonic stability problems, excessive reverse power flow, over voltage along distribution feeders. This is a typical problem that we have faced at IIT Roorkee also. So especially during the summer time, so we had purchased this power amplifier from German. So Germans, they don't understand the Indian dynamics. So there is very narrow voltage range violations feasible through this power amplifier. So plus or minus 10% or something like that. So, but especially the Roorkee grid, I don't know whether it's a big grid or strong grid. I didn't study, but the end result is that we suffered a lot because of the voltage fluctuations that we're seeing, especially during the summer time, because the solar panels which were placed at the rooftop, they were generating excess of energy. Then the load consumption was less because it's a summer time. Most of the labs were off, and students were also not there in the campus. So the lack of load and excess of energy, there is shoot up in the voltage. It was, I guess, it was more than 270 volts. We practically measured it. So then the power amplifier which was there was stripping off quite often, and then we had to bring a stabilizer to maintain the voltage. So over voltage along distribution feeders, especially the weak grid and the rural feeders, is quite challenging problem. Increased reactive power requirements uh, as you bring in more renewables in the system. So some reactive power requirements would be anyway there, even though in the case of W-fed induction machine, you place back-to-back converters, but they may not be able to meet out the expectations. Some reactive power consumption from the grid may be there all the time. So increased difficulty of voltage control, electromagnetic interference issues, and then difficulty of winding detections. These are some of the challenges that I mentioned. There could be more research problems as well. So rotor angle stability and rotor angle and small signal stability, system inertia reduction, electronics control strategies, changes in synchronous and damping control. So these are the research uh, works that are carried out in this area. Just a minute. And then the voltage stability issues like reduced reactive power reserve, and then the frequency stability issues because of inertia issues and the reduction in primary response, and the subsynchronous resonance, right? and oscillatory stability issues. This is there with the W-fed induction machine also, SSR. So I hope you all are familiar about this SSR issues because of series capacitor, and then there is a resonance that takes place, and that results in low short circuit impedance, and that's a challenging point. So application of power converters for voltage and frequency control by penetration of renewables. So you, with the help of renewables also, you can offer improved active and reactive power response, and maintain the frequency and voltage. Now we'll move on to the last phase of the presentation, which is the case studies. So before we jump in, so if there is any questions, you can ask. Is there any questions till now?
Participants, if you like to ask anything or discuss anything till this part, you can unmute yourself and you can ask. Okay, Gururaj sir, we can continue, I think.
Yeah, okay. So the last phase is real-time simulation. So the real-time simulation takes place uh, with the synchronized with the clock speed that you have in your room or watch or whatever. So whatever time, why do we need a simulation? The basic idea we need about going for a simulation is we try to understand the physical system in our own computer, because any solutions that we try to bring in, we cannot directly deploy into the field. So first we need to validate through theoretical analysis, then simulation, and then go for a hardware in loop case studies, and then do the digital twin modeling and try to really ascertain the practical dynamics or challenges that we may not foresee during the initial plan of our understanding the problem. But eventually, you don't want to create a huge negative impact. Sometimes, we say this thing that solution to the problem may be more challenging than the original problem itself. You come up with there's a problem and you come up with a solution, and the solution to the problem is more dangerous than the original problem. So that should not be the case, right? So the real-time simulation is really one step ahead than the conventional uh, uh, simulation techniques, where you try to model the system closely to the reality, accurate as accurate as possible to the real system, and then understand the dynamics basically, and come up with the good solutions where you can offer, which you can plug into the actual system. So there are various kind of real-time simulators seen, especially for power system engineers. So RTDS, Typhoon, and Opal. RTDS, we have different racks, and you have different cards available: analog output, input, digital input cards. So which are meant to communicate with the external hardware. You don't have to use these cards for the real-time simulation, but for the hardware in the loop case studies, so these cards are used uh, to sense the actual signals and communicate with the physical hardware prototype. On even otherwise, you can develop a good simulation network. I mean, the reasonably good size of simulation network, and then study various cases. Right. So it's mostly suitable for power system, but we have used it for power electronics applications, and we have got good results for the power electronics applications also. So, but most popular for the power system studies. And then there is a Typhoon Hill, which also has these facilities, and then mostly used for microgrid based applications, and then Opal RT is for good for power electronics based applications. So I'll discuss some of the case studies that we have done, especially for the application resiliency, right? So resiliency, what is resiliency? Resiliency uh, is a transient event, or a situation where you see that there is a sudden change in the generation demand pattern because of uh, because of could be a fault or a natural disaster, due to any reasons. If there is a sudden cutoff of power supply and system is seriously struggling to maintain the critical loads, so that is a resilient case. So the system is set or can be called out as a resilient system, depending upon the potential of that system to avoid a resilience event in the first go. And if the resilient event is inevitable, then how do you able to sustain? What is the flexible resources and management you have, so that you try to manage your existing resources and try to offer electricity to the most critical loads in the system. So then we call this system as a resilient event. And not only that, post event and how best you recover from the event. So avoiding the event, sustaining through the event, and then restoring the event is restoring or recovering from the event is what we call it as a resiliency. So uh, so we have done some analysis and research in this area. So you can see here that we have taken a small case study of a home where we have a solar photovoltaics and a wind and the battery of two types. One type of battery is connected to the UPS and another type of battery is connected to the electric vehicle. So and then you there is also G2V and B2G kind of uh, feasibility also being assumed here. So the objective is there are two types of battery chemistry. So we try to restore, maintain some state of charge, bare minimum state of charge in the mobile battery, and we prioritize these resources, try to extract maximum energy from solar and wind if during the steady state of operation, and then if these resources are not available, then use the energy from the grid, try to maintain charge in the batteries. And even among the batteries, we give more priority to the mobile battery because the mobile batteries can be employed uh, to if there is a requirement at the neighbor's home, we can use this vehicle as a small power source and then and try to support the neighbors as well. So this is a control scheme, and this just displays the different case scenarios, whether it's a grid connected or isolated kind of situation, and how we are managing our resources in prioritizing the resources in such a way that the maximum power is tracked and state of charge is maintained in the batteries. So these are the real-time simulation results. I think we have done this. We've taken these results from Opal, and then the change in the various dynamic situations like fault and then unbalance. You can see this is a fault condition, there is an unbalance, or there is a variation in solar photovoltaics power output. All these dynamics have been considered, and then the results have been taken out. So the observation is that um, assuming that we need to maintain a bare minimum loads like electric jackhammer, pressure ventilation fan, 10-liter soup kettle, intensive care medical ventilator, 100-watt LED floodlight. So these are the loads we assume that are necessary for a home to survive. Even if there is a national emergency, there is no electricity, there could be blackouts also. If you remember in 2012, we had a blackout for 3 days and the whole northern grids um, was under black, right? So uh, during such kind of emergency situations, if at all if we work out through the electric vehicles, so we propose that with the particular kind of control scheme that we have proposed, we could sustain for 6 days maintaining these loads, bare minimum loads, assuming that they are running for 24 hours as well, right? And then the AC microgrid, renewable and EV penetration in power system. This is another work that we have carried out to see the impact of EV in the power system. So we have used solar photovoltaics, RTDS based simulation that we have carried out, and there is a EV charging stations, electric storage of a stationary type is also part of the system. And then we increase the electric vehicle load on the power system, and we could see that there is a serious change in the voltage profile of the network. And This is a work on uh, coordinated voltage control, which I had done during my PhD. So this is also in a way connected to the resiliency. So I have taken this work. So this is IEEE 33 bus distribution system. We have it's a radial network. Many renewables are connected. So solar photovoltaics and wind are part of the system. Solar photovoltaics through a DC microgrid topology being connected at bus number 5, and there is a W-fed induction generator of type 3 wind turbine is connected to the bus number 22, and there is also DStatCom connected close to the same vicinity to support the DFIG during the fault rate through, and there is also on-load tap changing transformer which is seen at the bus number 1. So the objective of this study is that, so if due to some reasons, if there is a fault, and how best you can respond to restore the voltage. So this is a resilient event again. So, and during the steady state also and see, please understand the transient behavior depends on the planning stage, how you have planned during the steady state and dynamic situations. During the steady state, if you have not properly managed your flexible resources, then that will affect your performance during the transient event, right? So the objective here is to restore the voltage, because voltage restoration is the most important uh, thing that one would look forward for, especially during the transient or fault situation. So voltage restoration is connected to the reactive power management. So this whole ball game is about reactive power management. And the interesting point is we have achieved this reactive power management without coordinating or without establishing a physical communication across this voltage regulating devices, which are situated at bus number 22, bus number 5, and as OLTC situated at bus number 1. So this is a decentralized in the sense there is no communication, coordinate, though decentralized yet coordinated voltage control for the 33 bus distribution system. So uh, and the objective during the steady state and the dynamic situation is to have a better voltage profile. If you have a better voltage profile, my dear friends, then you can reduce the overall system losses, correct? So loss minimization is also an added advantage that we can perceive during the steady state operation. And then good amount of reactive power margin to be planned for the transient situation is the objective that we are planning for the steady state operation. And then the transient situation where you manage this reactive power reserves in such a way that you recover the voltage profile as quickly as possible. So we have defined 3 different states: a steady state where the reactive power requirement expected from the fast acting converters are considered to be less than 40% of their available capacity. And in the dynamic state, though the reactive power requirement is increased because of switching off some dynamic loads like motor loads, but we hard limit it to 40% to ensure that bare minimum reactive power margin is available for the transient situation. And the transient state where the 100% reactive power capacity available from the converters are used for the fault rate through behavior. So these are the 3 states that we have defined: steady state, dynamic, and transient state. Please understand that the OLTC, which is situated at bus number 1, has an operation range. That operation range is 0.9 per unit to 1.1 per unit. And how does OLTC operates? Let's say the OLTC is connected to bus number 1. Usually it gets connected to the mainstream bus. So bus number 1, and from there are 3-4 feeders which are carrying power to the different buses. So the OLTC is situated at bus number 1, and if there is any change in voltage perceived at bus number 1, and if the change in voltage has some significance, that means it's beyond the threshold value, and and uh, and 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 is seen or perceived for a good amount of time, some threshold time is also kept to ensure that if there is some sudden transients, and we should not change the taps frequently. As you can recall, in the earlier part of my discussion, I've already mentioned that mechanical OLTC tap changing is not so recommended more frequently because it will affect the life of OLTC tap changing. So you ensure that the significant amount of voltage changes happens for a considerable amount of time, and then this OLTC tap changing may be initiated. Now, so this is a conventional OLTC case scenario, but in this particular case study, we didn't assume a conventional mechanical OLTC, rather we have assumed a solid state transformer where there is no boundage of number of tap changings. Rather, we have, perhaps we have assumed that we don't want to change more consequently. The reason being, keep if we keep on changing the voltage profile, then that will affect the other sensitive loads as well. So we have kept a bare minimum time duration, and a threshold of voltage limits also being kept, and ensure that if the voltage change bypass or voltage change is there for significant amount of time, and then the voltage tap changing is initiated, but the limits of the operation range is 0.9 per unit to 1.1 per unit, right? So, but the converters, which are fast acting converters, which are connected to this renewables, so they don't have any range of operation. They can operate from any voltage range. Like for example, the fault rate through behavior from the German grid codes, as I've already mentioned. So they suggest zero voltage right through also, right? So from 0 per unit to 1 per unit, so you're supposed to operate. So there are two types of devices now. OLTC, which is quite sluggish. The sluggishness we have artificially created. Solid state transformer, they don't have any sluggishness. Sluggishness is there inherently in the mechanical voltage, right? Sluggishness we have added intentionally for the operation of a solid state transformer, but still we are considering it to be a sluggish voltage regulating device. And then there is a fast acting converters, which would um, which are fast in response, but the operation range is quite long. So the idea is, how do we manage these different voltage regulating devices, though there is no communication? So to ensure that the objectives are fulfilled. So in that case, if there is any small amount of reactive power being injected by these fast acting converters during steady state, so because it's a radial network, any amount of reactive power flowing through any corner of the network will also impact the other buses as well. So some reactive power injected because of fast response of the converters may avoid OLTC to complete its action. So that means we are not utilizing the OLTC during the normal operation or steady state operation. And on the other hand, we are also losing some capacity of the inverter, which otherwise would have been used during the transient operation. So this is the ball game. So to ensure that we find a solution, we have come up with a novel idea of introducing a delay before the operation of fast acting converters, such that that delay will avoid the fast acting converters to suddenly respond owing to any change in perturbation where these fast acting converters are connected, and then allowing the OLTC to smoothly complete its action. And then if at all, if it is necessary, then these fast acting converters are allowed to inject the reactive power. So this is the whole ball game. And then so this is the implementation of control scheme. I'll not go in detail again. So some more details are there, but in the interest of time. So this is the advantage. You can see there's a delay being inserted in the case of proposed technique. And then as compared to the existing schemes, so we have achieved the better voltage profile, and voltage recovery is also quicker because we have more reactive power margin. As you can see in these slides, you can see that there is because of delay, there is a good amount of reactive power margin available. And then the voltage recovery time is also less as compared to the existing methods. So this is the hardware validation of the control schemes. We have developed the DC microgrid power amplifier, and RTDS is also there. And then we have validated our results. So we have come, again improved our own control scheme, and then thought that, why do we need to keep our converters idle? Rather, we consume the reactive power during the ideal time. So that part is also included, and we saw better results compared to our own results. So and then the fault rate through scheme. So these are all very advanced research works. So where we have considered the fault to take place before the fault current limiter with respect to DFIG because of relay coordination. So in that aspect, if fault happens before the fault current limiter, and how do we address this issue? Because if fault happens after fault current limiter, naturally there is a fault rate through improvement. So one need not have to do any research. Enough research being already done. But due to some reasons, like for protection considerations, if the fault is situated, sorry, fault current limiter is placed far away from the placement of a DFIG, and then if fault happens in between the fault current limiter and the DFIG, and how do we address such kind of situations is what we also worked out. So many projects that we are handling currently, some students are also working. These are pretty old slides, but anyway, I've completed. Thank you very much. If there is any questions, I can take it up. Thank you. Over to Professor Vishal.
Thank you so much, Dr. Gururaj, for such an insightful and thought-provoking presentation. So now I request participants if they wish to ask anything to Dr. Gururaj regarding this session or presentation. Kindly unmute yourself and you can ask or interact with the Dr. Gururaj. Any participant? So thank you very much.
I hope the
Dr.
participants are there in the meeting. Thank you so much again, Professor Vishal, for this opportunity to interact with many of our colleagues.
So on behalf of organizing committee and all the participants, I extend our sincere gratitude for your valuable time, effort and contribution to this FDP program, Faculty Development Program. So definitely from this lecture, knowledge, idea you have shared will be greatly benefited in our academics as well as research work. Thank you once again, Dr. Gururaj.
Thank you, Professor Vishal.
So,
Again. Thank you. Bye.
with these words, I formally declare the completion of this particular session. So our next lecture will begin after the lunch at 2 p.m. So thank you everyone. Please join us again after the lunch for the next insightful session. Thank you. Thank you everyone.